All right, get ready to dive deep. Today we're tackling LSTM and how it's changing the game for stock price prediction. You've given us a ton of research, papers, and articles, some dense, some surprisingly easy to digest, but all pointing to the potential of LSTM.
It's a pretty impressive collection, and it shows how much interest there is in LSTM, especially in finance. It's fascinating. This type of recurrent neural network is really good at spotting patterns in time series data. Things like stock prices, things that traditional methods often miss, almost like it has a memory, seeing those connections across time.
Okay, that definitely has my attention. But let's back up a bit. What exactly is LSTM? What makes it work? I mean, I know it stands for long short-term memory, but what does that mean practically?
Well, you're right. The name is very descriptive. LSTM is all about remembering information over long periods, which is where typical recurrent neural networks have trouble. Think of it this way. Inside an LSTM network, there are units called cells. They're like little computers. Each cell has these control gates, the input, forget, and output gates, and they regulate the flow of information, almost like a system of valves, deciding what information is stored in the cell's memory and what goes through.
So these gates are choosing what the LSTM remembers and forgets. It's like it's learning selectively from the past. It seems pretty important for predicting the future, right?
Exactly. That selective memory is what gives LSTM an advantage. It can learn from long-term dependencies in the data, like how a company's past earnings, even years ago, might affect its future stock price.
That's really interesting. But you mentioned data quality is really important for LSTM, so we can't just feed it any old spreadsheet and expect it to give us winning stock picks.
You got it. LSTM is powerful, but it's only as good as the data it learns from. Think of it like a chef. You give them great ingredients, they make a fantastic meal. Give them bad ingredients, well.
Garbage in, garbage out. Right. But what kind of data are we talking about here? What does LSTM need?
LSTM works best with large data sets full of relevant info. We're talking historical stock prices, trading volume, economic indicators, the usual suspects. But it can go deeper, too. Things like news sentiment analysis, social media trends, even satellite images to see a company's activity level.
Wait, satellite images, that's incredible. So it's not just about the numbers, it's about understanding the bigger picture, the story behind the stock.
Exactly. That's where things like data preprocessing and feature selection become so important. One of the papers you gave us, a hybrid model to predict stock closing price using novel features and a fully modified Hodrick-Prescott filter, really highlights this. It talks about using a modified Hodrick-Prescott filter to smooth out noise in stock price data so the LSTM has a clearer signal to learn from.
That makes sense. You have to refine the raw data, like polishing a diamond.
What's even more interesting is that this study combined the LSTM with sentiment analysis from Twitter. They called it RNN plus FMHP plus scent. It was really effective. They compared it to other models, and it consistently did better. Shows how powerful a well-tuned LSTM can be.
RNN plus FMHP plus scent. All right, I'll try to remember that. So it's not just the LSTM itself. It's how you use it, what you combine it with, how you prepare the data. It's like making a suit. You need the right fabric, the right tailoring, and the right fit.
Exactly. And that brings us to another layer. The different LSTM architectures. It's not a one-size-fits-all thing. There are lots of options.
Oh, options.
Yeah.
I'm listening. Tell me about these different LSTM types. What's out there?
First, you've got your classic RNN LSTM, the foundation for many applications, kind of the original LSTM. And then you have some variations that build on that.
Okay. RN-LSTM, the classic. What else?
There's CNN LSTM, which combines convolutional neural networks, good for processing images, with LSTM for time series. So you can analyze stock charts, even company logos, for extra insights. Then there's bidirectional LSTM, which looks at both past and future data points, gives it a wider perspective on the market.
Wait, future data, isn't that like looking into the future?
Not exactly. It's more about understanding the context of the past and future to get a better view of the present, like understanding a word in a sentence by looking at the words before and after it.
Okay, I can see how those variations can offer different levels of insight, but how do we know which one is the right one to use?
That's the big question, and we'll explore that more as we dig deeper into your research. But first, we have a couple more LSTM architectures to add to our list. Dual-layer and single-layer LSTM. These are all about adjusting the complexity of the network to find the sweet spot between capturing patterns and avoiding overfitting.
Overfitting. I've heard that term, but can you explain it?
Imagine studying for a test and just memorizing the answers, but not actually understanding the material. You might ace that test, but you won't be able to use that knowledge anywhere else. That's basically overfitting. The model becomes too focused on the training data, and it can't handle new data well.
So it's like a student who crowns but can't actually think about the subject.
Exactly. And that's why picking the right LSTM architecture is so crucial. You need a model that's complex enough, but not so complex that it just memorizes instead of learning.
This is fascinating. We've covered so much already. LSTM, how it works, the importance of data, and now all these architectures. It feels like we're just getting started.
We are, and it gets even more interesting. Next, we'll look at how these architectures are used in finance and see if we can answer that big question. Which LSTM method is best for predicting stock prices?
I'm ready. Let's keep going.
So we've laid the groundwork for understanding LSTM and its variations. Now let's see how they're actually used in finance. Ready for some real-world applications?
Absolutely. Let's see how this theory translates into action. Give me some examples.
One area where LSTM is making waves is portfolio optimization. Imagine you're managing a fund, trying to build a portfolio that maximizes returns but minimizes risk. LSTM can analyze huge amounts of data, find subtle trends, even predict future asset performance to help make those tough decisions.
So instead of just relying on gut feelings, fund managers can use LSTM for a more data-driven approach. Seems like a game changer, especially with how volatile the market is.
Exactly. It's like having an extra set of eyes, maybe even a crystal ball, to help guide those choices. Another cool application is algorithmic trading. Those are automated strategies that execute trades super fast, like milliseconds, based on rules and signals.
Wow, that's amazing. So computers making split-second trading decisions based on what LSTM finds.
Right, and that's where LSTM is so powerful. It can process tons of data in real time, see tiny shifts in the market that a human might miss, and act on those insights incredibly fast, potentially making the most of short-lived opportunities.
It sounds almost too good to be true. But what about the risks? Are we putting too much trust in these algorithms?
That's a fair point. Algorithmic trading is powerful, but it has risks. There could be errors in the code, unexpected market events that the algorithm isn't prepared for, even things like flash crashes caused by a bunch of automated trades happening at once.
So double-edged sword. Exciting tech, but it needs to be used carefully.
Absolutely. It's not about replacing human traders completely. It's about giving them better tools and info to make smarter decisions.
Right. Okay, let's get back to the LSTM architectures. You mentioned RNN LSTM, CNN LSTM, bidirectional LSTM. Can you break those down and where they might be best used in finance?
Sure. RNN LSTM, that's the basic one, the foundation. It's really good for sequential data, like stock prices over time. The way it's structured, it can see those dependencies between data points across time, learning from past trends to predict the future.
So RNN LSTM, the workhorse for analyzing time series data in finance. What about CNN LSTM? What's its specialty?
CNN LSTM is great at using data that isn't just numbers. Like, think about analyzing stock charts for patterns, or using satellite images of a company's operations to see how active they are. CNNs are good at extracting features from images. Combine that with LSTM, and you get a broader view of a company's performance.
That's cool. It's like giving the LSTM eyes to see beyond just numbers. What about bidirectional LSTM? How does that work?
Bidirectional LSTM is all about context. It looks at data both ways, past and future, to really understand the present. Like, if you're trying to understand a word in a sentence, you look at the words around it. Same idea. Bidirectional LSTM considers both past and future trends in the market to get a more complete view of what's happening right now.
So it's like giving the LSTM a wider view. But with all these options, how do we choose the best architecture for predicting stock prices?
That's a great question, and researchers are still figuring that out. There isn't one answer. The best choice depends on the data, how far into the future you're trying to predict, and how you're measuring success.
So it depends on the specifics of what you're trying to do.
Right, but that doesn't mean we're totally lost. The research you have gives us some good clues about which architectures have done well in different situations.
Okay, that's good to know. Let's dive into some of those research findings and see what we can learn.
For example, one study, Binary Gravitational Search Algorithm and Support Vector Machine for Forecasting and Trading Stock Indices, looked at using a binary gravitational search algorithm to optimize the settings of a support vector machine model. It was about predicting whether a stock index would go up or down. Now, they didn't compare different LSTM architectures directly, but it shows how important it is to fine-tune models and try different optimization techniques to get the best results.
So even if there's no one best LSTM, we can optimize what we have to improve their accuracy.
Exactly. And that's what's so exciting. The field of LSTM in finance is constantly evolving. Researchers are trying new architectures, new data sources, new techniques to see what's possible.
Sounds like we're at the beginning of a very interesting journey. But before we get too far ahead, let's go back to those other two architectures. Dual layer and single layer LSTM. How do those fit in?
Dual layer and single layer LSTM are about finding the right level of complexity. If your data set is simple, a single layer LSTM might be enough. But if you have a lot of variables and complex relationships, a dual layer LSTM might be better at capturing those patterns.
So it's like choosing the right tool. You wouldn't use a sledgehammer to hang a picture, but you might need one to demolish a wall.
Exactly. It's about matching the tool to the job, and that's a big challenge in LSTM research. Finding that sweet spot between a model that's too simple and one that's so complex that it overfits and becomes less accurate.
This is making me think about the whole idea of predicting things. Even with amazing tools like LSTM, can we really predict the stock market? Or is there always some randomness, some uncertainty that we can't account for?
That's a big question, one that's been around for a long time. The stock market is complicated. It's affected by so many things, and many of those are impossible to predict with perfect accuracy.
So even with all this amazing technology, we're still dealing with probabilities, possibilities, not certainties.
That's right. But that's what makes this field so fascinating. It's a constant challenge trying to understand the market and develop tools to help us navigate it.
Well said. I'm ready to see what else we can find in the research. So we've explored a lot about LSTM for stock prediction. We've seen how it works, the different architectures, the real-world uses. We even talked about the big question, can we really predict the market?
It's been a great discussion, and honestly, we've just scratched the surface. LSTM is still pretty new. There's so much more to learn and discover.
I'm really interested in those research papers comparing the different LSTM architectures. What did they find? Any clear winners for predicting stock prices?
Well, like we said before, there isn't one best architecture. It really depends on the specific problem, the data you have, and how you're measuring success. But the research does give us some interesting insights.
Okay, what are the highlights? What are the researchers saying?
One study you gave us, a hybrid model to predict stock closing price using novel features and a fully modified Hodrick-Prescott filter, really stands out. Remember that RNN plus FMHP plus scent model?
The one that uses sentiment analysis from Twitter? Yeah, right.
Right. That model consistently did better than others in terms of prediction accuracy. The researchers said it was because of a few things. The RNN LSTM foundation, using the modified Hodrick-Prescott filter to smooth out the data, and including that sentiment analysis, this model was really good at capturing both the numbers and the feelings driving stock prices.
So it combines technical analysis with market psychology. A winning formula.
Exactly. And this study shows how important it is to use different techniques and data sources to build a more complete and accurate model.
We've talked a lot about using LSTM to predict stock prices. But what about its limitations? Are there times when LSTM might not be the best tool?
That's a great point. No model is perfect. LSTM, like any machine learning algorithm, has its limits.
Can you give some examples?
Well, one big challenge is dealing with unpredictable events. Those black swan events that you can't see coming based on past patterns. LSTM models learn from historical data, so they might not be able to accurately predict things that have never happened before.
So it's like trying to predict the future just by looking at the past. You might see some trends, but you'll miss those unexpected events.
Exactly, and that's where human judgment is still so important. Even with the most advanced LSTM models, we still need human analysts to understand the results, look at the bigger picture, and make smart decisions.
It sounds like it's about machines and humans working together.
I think that's the future of finance. We need to use the power of technology, but also recognize the importance of human expertise.
Well said. This deep dive has been really insightful. We've learned so much about LSTM, its different forms, its uses, and even its weaknesses.
And like I said, we've only just scratched the surface. There's so much more to come in the field of LSTM in finance. Who knows what breakthroughs are coming next?
Maybe one of our listeners will create the next big LSTM model. They certainly have the knowledge now.
They do. This deep dive has given everyone a solid understanding of LSTM and what it can do. It's an exciting field with endless possibilities.
To all our listeners, keep exploring this technology. Stay curious, keep experimenting, and who knows, you might be the one to figure out the stock market.
Remember, learning never stops. There's always something new to discover.
Well said. Thanks for joining us for this deep dive into LSTM. Subscribe for more explorations of cutting-edge technology. Until next time, stay curious.